Hello, we are from Group 2 Subgroup 8. We will be presenting journal reflection entitled Bioremediation of Soil Contaminated with Diesel and Biodiesel Fuel using Biostimulation with Microalgae Biomass. In this journal, there are three research objectives. First, to evaluate bioremediation of soil contaminated with oily compounds, diesel and biodiesel using biostimulation approach and compare its effectiveness with natural attenuation. Second, to characterize the phycocyanin as bioemulsifier. Third, to compare effectiveness of phycocyanin with other biostimulants, spirulina biomass and ammonium sulphate. For the method, first, soil was prepared by contaminated with 4% oily compound, diesel or biodiesel, and placed in 20 glass bottles and each containing 300 grams of soil. Second, biostimulants were prepared before adding to the soil samples. Third, biosurfactant activity of phycocyanin was characterized by determining emulsification activity using aqueous crude extract of phycocyanin before lyophilization. Next, the experiments of bioremediation were performed in replicates without the addition of biostimulants to stimulate natural attenuation to verify the effect of biostimulants on the microbioactivity and the process of degradation of contaminant. Then, the assessment of bioremediation was performed in triplicate with the addition of biostimulants to evaluate the biodegradation. Lastly, the results were presented by ANOVA, and the means were compared by Turkish test at 5% significant level.
Next, we are going through the results of the experiment. The biosurfactant activity of crude extract of phycocyanin was measured by determining the emulsification activity of oil in water and water in oil of phycocyanin extract by using the formula as shown on the screen. For the formula of emulsification activity of oil in water, the absorbance of both phycocyanin extract and blank were measured by using a spectrophotometer at 610 nanometer. The total height and emulsion height of water in oil mixture were measured and water in oil emulsification activity was determined. T stands for dilution of phycocyanin extract in distilled water. So, the result showed that the emulsification of oil in water is 2.80 plus minus 0.07 emulsification unit. And emulsification activity of water in oil is 225.8 plus minus 3.14 emulsification unit. So, we can see that emulsification activity water in oil values for phycocyanin were higher compared to emulsification activity oil in water values.
This has also been demonstrated in other research that biosurfactant produced by in-solid-state fermentation by using the fungi aspergillus fumigators obtain an emulsifying activity water in oil of 144.5 UE higher than oil in water emulsifying activity. Surfactants are amphiphilic molecules and they have a natural tendency to go to oil-water interface.
Next slide is about the results of bioremediation assays. The quantification of carbon dioxide evolution is an indicator of microbial respiration. And according to Silva et al. 2009, it also can provide information about the biodegradability of hydrocarbons in contaminated soil. Sansikin et al. 2007 also mentioned that the amount of carbon dioxide emitted is proportional to the biodegradability of the substrate.
Quantification of release CO2 is one way to evaluate the microbial metabolic activity in soil under aerobic conditions. It is indicative of the degree of mineralization of contaminant in the substrates and therefore the complete degradations thereof.
We can see Figure 1 is a graph relationship between carbon dioxide evolution along 60 days of bioremediation. Basically, the bioremediation period is divided into two periods. There are 0 to 30 days and 31 to 60 days. Based on the graph in Figure 1, we found that the rate of evolution of carbon dioxide was higher in the first period, 0 to 30 days, for all the experiments that were biostimulated. The lines 1 to 10 in Figure 1 indicate the experiments which the contaminant were being biostimulated. So, at the end of the bioremediation, the rates of carbon dioxide evolution in these experiments decrease. In the experiments of natural attenuation and in the controls, the highest rates of carbon dioxide evolution were observed in the second period of bioremediation, 31 to 60 days. It is shown in line 9 and 10 in Figure 1.
The rate of evolution of CO2 was higher in the first period, from 0 to 30 days for all the experiments that were biostimulated. This behavior may be attributed to the use of ammonium sulphate, microalgae biomass, or phycocyanin as biostimulants, as they may have increased the population of microorganisms and caused the increased rate of CO2 evolution. At the end of the bioremediation, the rates of CO2 evolution in these experiments decreased, possibly as a result of the decrease in the biostimulants and contaminant concentrations, which served as a carbon source for microorganisms. In the experiments of natural attenuations and in the controls, the highest rates of CO2 evolution were observed in the second period of bioremediation, from 31st days to 60 days, probably because of the lower microbial population and longer adaptation of organisms to contaminants as reported by other researchers.
In Table 1, we found that the experiments that use biodiesel as a contaminant, the maximum cumulative carbon dioxide evolution values were 2,997.35, 2,882.90, and 2,763.73 milligram carbon dioxide with the phycocyanin biomass of spirulina and ammonium sulphate respectively. When diesel was the contaminant, the maximum carbon dioxide evolution was obtained with the biomass of spirulina as the biostimulant, followed by phycocyanin and ammonium sulphate.
Several researchers have reported that biostimulation promotes the growth of microorganisms, which leads to higher CO2 evolution. They concluded that biostimulation accelerated the mineralization of diesel and decreased the concentration of total residue petroleum hydrocarbons. The organic biostimulant produced better results than the inorganic one. Ammonium sulphate, although phycocyanin was added in smaller amounts than the ammonium sulphate and spirulina biomass, the values of evolved CO2 that it produced were higher, probably because the organic carbon sources are more readily available for use by the microorganisms. Furthermore, as spirulina biomass and phycocyanin contain carbon, a portion of carbon evolved in the form of CO2 may have been caused by the use of biostimulant as a carbon source by the microorganisms, as that contributes to the generation of energy for microbial growth.
The table here shows the removal of the contaminant by using the biostimulant. For biodiesel contaminated soil, the removal of the contaminant was 86.1 to 88.7% with no significant differences, probability less than 0.05, among the biostimulants that were used in the study. However, significant differences, more than 0.05 compared with the assays conducted by using natural attenuation, 42.3%. For the soil contaminated with diesel, the biodegradations range from 53.1 to 63.9% with significant difference, probability more than 0.05, between the biostimulants used and compared with the assays accomplished through natural attenuation of 31.3%. It shows that the biostimulation is better than from natural attenuation.
The amount of degraded contaminant may be underestimated if part of the degraded organic material is used for the production of biomass, or overestimated if the CO2 produced from the degradation of any carbon source available in the soil than the contaminant. Therefore, in addition to CO2, the biodegradation of diesel and biodiesel was also evaluated through the quantification of oils and grease. The higher biodegradation of biodiesel compared with diesel can be explained by the metabolic pathways by which these contaminants are degraded. Biodiesel is a fuel derived from vegetable or animal oils, usually composed of fatty acid, methyl esters, and long chain. In this biodegradation process, the fatty acids are converted directly to acetyl-CoA by beta oxidation for subsequent conversion to CO2 through the Krebs cycle, whereas the aromatic compounds present in the diesel oil involve the conversion of the aromatic substrate in a metabolic such as catechol with subsequent ring opening by enzymes called deoxygenases and conversion of the compounds as acetyl-CoA, oxalate, and pyruvate, which are intermediates of the respiratory process.
There are many conclusions that can be applied from this journal. First, degradation was more efficient when compared with natural attenuation. Second, organic biostimulants were effective and show potential for application in the bioremediation of soils contaminated with oil residues. Third, the extractor of phycocyanin of spirulina was the most effective biostimulant as it had the greatest influence on the evolution of carbon dioxide by soil microorganisms. Next, the phycocyanin is shown to exhibit surfactant activity that can aid in the bioremediation processes. And the last one, novel compounds may be used as biostimulants in bioremediation of soils contaminated with oily compounds.
Meanwhile, there are limitations of the research. Firstly, the research are only limited and applicable for ex situ condition. Secondly, delivery and transport of the biostimulant to subsurface soil contaminant is not yet evaluated. And finally, the other environmental factors such as rainfall that could affect the experiment is not being investigated together. Benefits of the research. Firstly, the study can be applied to design enhanced bioremediation strategies in biodiesel and diesel. Secondly, spirulina biomass and its compound, biocyanin, can be extracted easily and used in oil biodegradation because both are effective. Thirdly, biostimulation was more practical than natural attenuation because it promotes carbon dioxide release in microbes. As we know, carbon dioxide is one of the parameters in bioremediation. Lastly, the use of microalgae as an alternative way of oil compound has become more widely applicable and convenient.
Reflection. Suggestions for future improvement. The study discovered that phycocyanin from spirulina work best as biostimulant. For future studies, there are several improvements to be made. 1. A strategy for in situ bioremediation must be developed. The study has developed an effective way of treating soil via ex situ bioremediation, but has not taken in situ bioremediation into consideration. 2. Other microalgae besides spirulina can be tested for efficiency, such as chlorella. Although the study proved phycocyanin extracted from spirulina is an effective biostimulant, Alternatives for spirulina should be discovered as well to expand the available sources of effective biostimulants.